Hello everyone, let's get to the lecture third. And in this lecture, we'll be going over tensor parallelism and sequence parallelism. Let's get to the slides. Before jumping into tensor parallelism, let's start understanding why it is necessary. In the last lecture for data parallelism, we discussed about optimizers, gradients, and weights, and how we can shard them to conserve memory and train really large models. But there is another component that plays a role in spiking up your memory consumption. That's called as activations. Activations are basically the intermediate results that you store after a multi-layer perceptron layer or any matrix multiplication so that you can do backward pass. And in most of the cases, you need to store these activations so that you can do backward pass. And there are other methods like activation, checkpointing, or recomputation. In activation checkpointing, instead of saving all the intermediate activations, you just save some of them, um, and that depends on how difficult was it to compute, and and for rest of them you just recompute it during your backward pass. And as uh, computational power uh, computational power is not the bottleneck, memory is the bottleneck, so you can discard the intermediate activations and recompute them during your backward pass, and you can conserve activations that way. Or you can so these are like the two methods, recomputing or um, checkpointing. And and before going into understanding tensor parallelism, also we would like to have a dummy example of finding out what's the total activations in a mini transformer. So let's first go through some of the notations. First is A, which is number of attention heads. So in multi-headed attention, we have multiple attention heads, and that's how we are going to calculate the query key and value, and thus the attention. And B is the micro batch size, and H is the hidden dimension size. It stays the same across all the transformer layers. And L is the number of layers in transformer, and V is the vocabulary size. So so you so first, to the transformer, the model has to go through an embedding layer. Let's see how does the embedding layer function. So embedding layer gets an input of mini batch size and sequence length, and each sequence length is basically a token ID. So this token ID will correspond to the first row in this matrix, and this one would correspond to the second row in this matrix. And you would basically do a torch.allGather on this embedding layer to convert the token IDs to hidden dimension, which is of batch size, comma sequence length, comma hidden dimension. After that, before even we start doing self attention for the first layer, we start with a layer norm in a transformer block. And in layer norm, we have mean and variance, and the mean and variance are unique for a batch size, because you'll be um, mean and variance are basically for each hidden dimensions. So you need to store those activations so that you can do backward pass on mean and variance, because those are also learned. But for our calculation, we'll be ignoring the mean and variance, as the hidden size is generally much larger as compared to the factor 2 here. So we'll be just ignoring the mean and variance, and we'll be just considering 2 SPH. And to calculate memory, we'll be using BF16, uh, so which has 2 bytes, hence the factor 2 here. And Also, one more thing to mention is if you have RMS norm instead of layer norm, then you don't have this mean component. So you basically have SB, only the variance is SB. Uh, so so like RMS norms gets rid of the mean part. So in layer norm, we'll only consider the input activations, and it will come down to 2 SPH, and we will just ignore the mean and variance here. And then we have to go to attention. Attention is a bit more complicated, and there are like a lot of things happening in this slide, so let's break it down slowly. Let's consider you have two attention heads. So this is your input size, which is 2 SPH, which is sequence length, batch size, and hidden dimension, and 2 is for you're storing in BF16 precision format. And then you have these projection heads, WQ, WQ1, WQ2, and WK1, WK2, which are basically different heads. And just for visualization purpose, we have taken two heads. So hence, you will take the input matrix and multiply with WQ1, do a matrix multiplication, and WQ2, and you will get back this Q1 and Q2. And these are basically, as we have two attention heads, so your projection would have half number of columns. So if you concatenate them, so for all the queries in across all the attention heads, your total activations will be 2 times this number, which is 2 SPH, and 2 comes from Q1 and Q2. Similarly, for K1 and K2, you have 2 SPH divided by 2, and if you combine the activations from these two attention heads, it will be 2 SPH. So queries and keys output the same number of activations, just that like they have like different heads, and all the heads pay attention to each other separately. So here Q1 and K1 belong to the first head, so they would pay attention to each other, which would be Q1 comma K1 transpose, which will produce a S cross S matrix. And this is where we apply the causal language model. So if you are training a causal language model like GPT-2, so here you will apply the causal mask, where the model, the first token will only pay attention to itself, and in the second only attention is paid till whatever we had, till that number, uh, till that sequence ID, and for the last one it will pay attention to for all of them. So and then after that we apply softmax row wise. So you need to apply softmax on this matrix after applying your causal mask, and similarly for this matrix you need to apply causal mask and then attention, and then do softmax. So if you see the number of activations from here, when you multiply S comma H by 2 matrix with S comma H by 2 matrix, you here you have to take the transpose of K1, you will basically get a S cross S matrix, and hence your total activation size would be S square B. And this is given for all the attention heads. So this second attention head will follow similar method, and it will also produce S square B matrix. So the total would be 2 into, and we have two attention heads, so S square B, or in our notations we had A attention heads, so it is 2A S square B. So each attention between query and key produces 2S square B, and for all of our across all our attention heads we produce 2S square B. And one more thing to note is this WQ1 and WQ2 are not uh, like standalone matrices. They are generally structured this way, where WQ1 and WQ2 are basically, you can do a sharding along the columns and you will get back the matrices. And this is going to be important when we look at the code. So this is all about the attention part, and this is the causal language masking that I explained. Okay, so after we went through the journey for queries and keys, so these are the, let's go through the journey for values. And this input matrix is shared by queries, keys, and values. And we need to transform this matrix for values, and these are the learned weights for the first attention head, and these are for the second attention head. And then you do a matrix multiplication and you get the value for first attention head and the second attention head. And they are as you have two attention head, hence your hidden dimension goes reduces by a factor of 2. And then we take this, and for the first head we multiply with what we had here, this q1 k1 transpose, which is s comma s matrix, and we multiply with it, and then we divide by the hidden dimension, and then we take the softmax and then multiply with this v1. So this would be your attention matrix for the first head. And similarly for the second head, you would have something similar like this, and here q2 and k2, this matrix, which is a s cos s matrix, goes into calculating the attention for this second head. And after that, these two matrices are basically combined to get back the full attention matrix, and you would have a s comma h matrix again, which is passed to the next transformer layer. So transformer is very homogeneous, like the input shape in and input shape out is same, which is like really good for parallelism, and you have predictable shapes. So this is the journey for attention. And if we just quickly look at our activations computation, it is 2sb h by 2 for this first attention head, and we need to save the second attention head, but the total is 2sb h. And so I would really encourage you to go through the paper Reducing Activations Memory by NVIDIA, and this tutorial was basically following that paper. And this tutorial kind of deviates from that paper in these two aspects. Here they add two more attention memory, and I don't think like most of the language models use this architecture more anymore. So they also have a softmax dropout on this matrix. So if you have like this S cross S matrix, they would do a softmax dropout on this. And so dropout is basically you, from your S cross S matrix, you drop some of the values which will before taking the softmax. And it is a s square b. A comes from the attention head, s is the sequence length, and we have a s cross s matrix, hence we have a s square, and b is the batch size. So for each attention head we have a soft dropout, and there is no factor of 2 here, because dropout is basically ones and 0. It's a mask, hence it's an integer, so we don't need to store 2 bytes. So integers are like single bytes precisions. And also, like after taking softmax, you need to store those activations too, hence this extra 2s square b will also come. So in additions to this 2a square b, which we had earlier from before calculating the softmax, uh, you also need to have uh, like those dropouts and then post softmax. So this value is just after taking the softmax, you have this much activations, but then if you plan to apply dropout and then softmax, then you need to also consider those extra things that you are going to pay for. And after the attention layer, then we have the MLP layer. MLP layers are generally more straightforward. So you have, from your attention, we send in, like as I said, attention is very homogeneous, so you send in 2 SPH activations, and this will go through all our MLP layers. So in MLP layers, we basically up project and then apply a linear activation, and then we down project. So your generally your dimensions go from H to 4H and then 4H back to H, and in the middle you will apply GALU non-linear activations. So if you see here, you need to store this activations, which is basically as you're like expanding into 4 times, so it's like 4 SPH, and your precision is BF16, hence this 2 factor will come up. And also like after applying GALU, you need to store post GALU activations, hence this 8 SPH will come up. And after getting then you will get back the results, and you will immediately apply dropout. And as I said, like dropout is just mask of ones and zero with one one bytes of precision, hence you'll just need to store SBH for dropout. So the total activations comes around here it is 8, 8, 16, 18 and 1, it's like 19. And this, after you do the dropout, you will send in again SBH activations, and as your precision is PF16, so it is total 2 SPH, and this will again go through another post layer norm. And as I said earlier, we are going to ignore the mean and variance, so we are just going to ignore the activations for mean and variance, and we'll just be considering this 2 SPH that goes into layer norm. So that was a long way of saying looking at the total activations. Please feel free to go through the derivations above and see if it makes sense to you. And so here I just have a consolidated PowerPoint of all the activations that originated in our transformer journey. And so if you sum this up, this would come around 34 SPH plus 2a square b. And and if you refer to this paper, reducing activations memory paper, so they have this SPH 34, we got this factor right, but they have this extra 5 as a square b. If you just multiply h here, it will like cancel out. So this comes from the fact that I mentioned about here on softmax dropout and attention. And I don't think many open models that we have now use this. So this is the 3 a square b that comes from here, and I don't think many of the open models use this, and I chose to ignore that part. So if you just like add that part, then this extra 3a square b will come up, and you can match this expression in the paper. So this is the activations that you get, total activations that you get from like if you don't intend to do any activation checkpointing or activation recomputation, so this will be your total activations, and this will be going to be multiplied with the number of transformer layers, which is L. So if you see here, it scales by the sequence length S square, and if you want to train like longer sequences, this activation memory is going to shoot up a lot. So um, activations memory generally do not dominate in smaller sequence length. There you have to worry about data parallelism and getting your optimizers, gradients, and weights sharded. But as you increase the sequence length, which happens during pre-training, you train with longer sequences. You need to take care of this exploding sequence length and activations memory, and this that brings us into discussing about tensor parallelism. Okay, now let's get into tensor parallelism. And so tensor parallelism comes in two basic flavor, uh, called as column parallel and row parallel. And let's first try to understand column parallel. So this is a graphics that I took from PyTorch Lightning docs, and here, we generally apply tensor parallelism for matrix multiplication. So suppose you have a 2 cross 4 matrix and you are multiplying with a 4 cross 4 weight matrix. So in column parallelism, you take the weight and slice it uh, along the column dimension, and you slice it by the half. So because we have two GPUs, hence on first GPU you only have this, and on second GPU only have the latest stage. Then we take this input and we broadcast this to two two of our GPUs, and this is the collective communication in parallelism, where in broadcast you just take one data and just like broadcast it to all the nodes, and here we only have two nodes, so hence we just broadcast it to two GPUs. Then we do matrix multiplication for this chunk and this chunk and this chunk and this chunk, and then we get back two separate chunks, um, and then after that we can do a collective communication of all gather. So in all gather, suppose your first GPU has this data A, and second GPU has data B, and third GPU has data C. But if you want all the GPUs to have the same data in the same order, then you can do an all gather where uh, node 1 will get the data B and C from node 2 and 3 respectively, and it will be A comma B comma C. So here we will do an all gather between these two GPUs to have a consolidated matrix. So we have two communications here. One is broadcast to two GPUs, the input matrix, and 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 we need to do an all gather on the output. So we have two communications here. Now let's jump into row parallel. Similarly, in row parallel, uh, you need to cut the matrix by half here, yeah, along this row dimension. So your matrix would be half here, and the other half would be here, and and so now you also have to cut the input matrix into its subsequent parts, so that you can do a valid matrix multiplication, because in matrix multiplication these row will multiply with this column, and as there are only two columns here, so you can only multiply with two rows. So you need to divide the input matrix, and for that we use a scatter collective communication, where suppose this ABC are our input matrix, and we just want the first node to have A, second node to have B, and third node to have C. So you can just do a scatter operation, and you can like send from this source to all these three destinations. So this is doing a scatter operation where this part is going to first GPU and this part is going to the second GPU. So this So this part will go to the first GPU and second GPU, and now we have sliced the matrix, the yellow matrix. So we will do a matrix multiplication independently for all the GPUs, and now you have to accumulate the results, because here you only get the upper half, and you get both the halves, but these are like partial results. So you need to do an all reduce, and in all reduce you have multiple data in different GPUs, but you want to do an operation on this data, and then uh, broadcast it into all the GPUs. And also keep in mind that this operation can only be commutative in nature, um, or associative. So and the reason is, if you keep it as subtraction, like the data from these GPUs can arrive in any order, and it might lead to error in your computation. So this can only be addition or multiplication. So here the all reduce will be additions, because in matrix multiplication we add after we do the multiplication for a column and a row. So you will do an sum all reduce here to get back the original matrix. So so these are the two, r- column parallel and row parallel in tensor parallelism. Now you can also combine these two. uh, let's see what's the journey for that. So suppose you have a input matrix which 2 cross 4, and you first want to do column parallel, then followed by row parallel. So what you can do is you can take this matrix, and first you need to do broadcast, as mentioned here. In column parallel you first need to do broadcast the input matrix to both the GPUs. So you broadcast the input matrix, and then you break the input wet matrix, the yellow matrix, into two columns. uh, this is the first part and this is the second part, and then you do matrix multiplications uh, individually in both the GPUs. And then uh, you don't need to do uh, any all gather that we had here in column parallel, because you still have another operation of row parallel. So, and if you remember, in row parallel we had to scatter this input matrix into two GPUs, like the first part goes to GPU 1, second part goes to GPU 2, and in column parallel you basically get that free out of the box. So you don't need any communication here. And also, um, in in the MLP layer that I showed you here, we apply GELU nonlinear activation. And the good thing about GELU and all the activation, like the activation functions are there, they are element wise. So if I go back to my slide, so you can apply GELU activations on each of these elements here. uh, and and that is not and that can like stay independent, because it is like element wise. So in in the two GPUs you can independently apply GELU, and then you again do row parallel matrix multiplication, where you pass this part, do a matrix multiplication with this, and take this part and do a matrix multiplication here, and then you can do a all reduce add on these two matrices to get the final matrix. So one thing I skimmed over is going over column parallel and row parallel. So now you can like visualize, like there are four possible combinations. It can be either column and row, row or column, column column, or row row. So we can have like four possibilities, but this GALU activation kind of makes it more complicated. So if I go back here, so suppose you substitute this first one as row parallel, and in row parallel, like the matrices that we get back. So if I go here, the matrices you get back need to be summed before sending, like to have numerical correctness they need to have a communication. But if you apply GALU on this and on this separately and then try to sum it, you are going to face errors, like because GALU is non-linear, so you cannot like sum them after taking GALU, and or the identities that I wrote here is like if you take GALU of matrix multiplication, suppose this is for GPU1 and this is for GPU2, and it is not necessarily is going to be equal if you do an all reduce and then do GALU, which we should be doing because we want numerical correctness and we want GALU of the sum of them. But so that will incur a communication that we need to do. If you keep your row parallel at the starting, you need to do a communication because else this condition won't help. But for column parallel, we are basically doing an all gather, which is basically a concatenation operation. So that is independent of GALU because that is element wise. So GALU is not going to affect because you are not taking any sum on the matrices. So because of this property, column parallel is preferred on the starting. It's actually correct in the starting for numerical correctness, and row parallel or it can be column parallel at the second. So hence if you start with row parallel, we need to do a sum or reduce, and we need to incur a communication overhead there, because we cannot we cannot take GALU, we cannot take those two matrices separately, take GALU and then add them back. It's not going to be correct. So we are out of our four combinations, like the second and fourth are we can do those because of numerical correctness. So we can only do a column, row, and column. So from our column and column row, let's see which one would be more preferred. So please check out this source on Tensor Parallelism by Ferdinand Maum. It's like a really good video on Tensor Parallelism, and yeah, I'll be basically summarizing what I learned from that video. So here let's take the input matrix, and for column parallel you need to broadcast it first. In column parallel you need to broadcast it. So in column parallel, first you need to broadcast the input matrix on these two, and this is our weight matrix on the first GPU and this is the weight matrix on the second GPU. So these are basically like concatenated like 10, 20, 30, 40, and these are like separated out and they are put in two different GPUs. So first you do a matrix multiplication where 0 into 10 plus 1 into 20, so you get back this 20. And if you have to go through another example, 2 into 10 plus 3 into 20, you get back this 80. So you get this matrix. Now this matrix is not it's just like for the first column in the weights, and this is for the second column in the weights. So you need to have the full matrix, because if you see here, you need to broadcast the same input to both of these devices. So you need to do an all gather communication where you combine the result, and then you need to do a broadcast again to make it column linear again, the column tensor parallelism. So you'll incur a communication of all gather and then broadcast again, and then you will again go through the same process of how we went through here, and then you need to do an all gather at the end. So if you see here, there are like 4 communications, and this is because column parallel needs the entire input matrix to be broadcasted to the GPUs. You need to do this all gather. But if you, as we discussed earlier, column linear and row linear, so you take the weight matrix, you broadcast it, and then you do matrix multiplication with this sharded columns, and now you don't need to do any communications here, because row parallel expects a scatter operation. So if I go back here, row parallel expects that the first GPU only has this part and the second GPU has this part, so it expects a scatter operation. And if I see here, this is already divided, like the first column is here and the second column matrix multiplication is here. And now you can apply GALU on this, and then uh, you can do a matrix multiplication here. So this matrix multiplication will work by broadcasting. This column is repeated twice, and this column is repeated twice too. So you multiply 20 into 1 and 20 into 3, so you get 20 and 60 here, 80 into 1 and 80 into 3, 80 into 40 here. So these are like the tensor broadcasting rules, and this is how we do a matrix multiplication on this column vector and this row vector, and we get back this matrix. And now, as we discussed in row parallel, you need to do an all reduce by taking the sum. So this 20 is added with 80, and you get this 100. This 60 is added with 160, and you get this 220. So so if you see here, as compared to the earlier example, here we needed like 4 communications, and here we only need 2 communications. So hence we generally will be using column and row, and this is only valid for MLP layer. So if I go back to my MLP diagram, so here you can have this one to be column parallel, and then you apply GALU, and this one to be row parallel, and this is how your MLP will be structured for tensor parallelism. Okay, so this was only for the MLP layer that we discussed. Now we also need tensor parallelism for the attention. So this is the figure that we had earlier, where you take the input matrix, do a projection for different heads and for queries and keys, and then you, for each head, you do a matrix multiplication to get the attention, then you take the softmax, and then you multiply with the value vector. So so if you see here, this very nicely divides for having tensor parallelism, where you can have each head in different GPUs. So the first head can go to GPU 1 and the second head can go to GPU 2. Similarly, the first query key head can go to GPU 1, and the key head 2 can go to GPU 2. So in that case, as these operations like Q1 needs K1 and V1, so if I go here, similarly, like the first head for value stays in GPU 1 and second head stays in GPU 2, and you can just like multiply here. And you can just like multiply K1 transpose, and there is a error which I should fix, so that softmax, and then you take multiply with V1. So the hidden dimension is basically edge. I just did a mistake here, but it's good to fix mistakes so that we can learn together. And so this value stays in GPU 1 and this value stays in GPU 2, and now you can see like each GPU has its own activations to manage, and you do not spike the memory in each GPU. uh, so attention basically, multi-head attention basically fits in like really well for tensor parallel, because you do independent operations on each head, so you can like see that each head can reside on its own GPU. So, and also you need to care that the world size should be divisible by number of heads. Like you cannot have 3 GPUs if you have like 2 heads, or um, so it should be like a multiple of number of heads. Okay, now and we went over how to do tensor parallelism for attention MLP layer, and there is one more thing that we can have tensor parallelism on, and it is called as and it is the embedding layers. So if I have to go back to our embedding layers, uh, what embedding layers do. So the embedding layers basically take your batch of sequences which have token IDs, and each token ID correspond to a row in this embedding layer. So based on whatever token IDs you have, you just block out those rows, and you build your batch sequence length and hidden dimension vector matrix. So embedding layers are basically lookup table for having a representation for each token in your vocabulary. So let's see how we can adapt tensor parallelism in embedding layers. So in the tensor parallelism embedding layer, we call this as vocab parallel embedding. And this example will also be based on the example that I saw on 49 Mom's video on tensor parallelism, which is a great video. And here, like suppose you have a vocab size of 6, and you have these six embeddings in your vocab, and which are basically like the indices 0, 1, 2, 3, 4, 5. And what you will get as input is a list of indices, and you have to pluck out those indices from your embeddings. Like suppose 1 corresponds to 20, you pluck out 20. 4 corresponds to 50, you pluck out 50. And let's see how we can have tensor parallelism here. So in tensor parallelism, you'll just like divide the first 3 to be in the first GPU and the last 3 to be in the second GPU, and but you still have this indices vector which you need to plug out the embeddings. So for this indices x equal to 1425, so you go to GPU 1, and GPU 1 has a range of 0 to 2. So it has index 0 and 1 and 2. So this is index 0. 0 to 2 is in GPU 1. 3 to 5 is in GPU 2. So this is what I wrote here. Embedding GPU 2 is range 3 to 5, and embedding GPU 1 is 0 to 2. So you see based on this x 1425 what lies inside this range, and you build this mask. So you see first 1 lies inside 0 to 2, yes, hence true. 4 lies 0 to 2, no, hence false. 2 lies 0 to 2, hence it's true. 5 doesn't lie, hence it is false. So you take this and you multiply with your indices vector, and you get 1, 0, 2, 0. And now you need to subtract the lower range from each of these indices. And here it doesn't matter because it is like 0, but it will be clear in our next GPU. So you take the indices and then subtract the lower range, and you get back the same index actually, because the range is 0 here. And now you have 10, 20, 30, and you need to plug out this indices 1, 0, 2, 0. if you see the first index, it is 20, so you have 20 here. If you see this, the second one is 0, so this is 10, and you pluck out here. And this is 2, this is the 30th, so you pluck out here. And this is 0, and this is 10, you pluck out this one. And now you get this 20, 10, 30, 10 matrix. But remember, like these false were basically the indices that lied outside the range. So we will just multiply this matrix with the x mask, or the mask that we generated here. So these matrices will be zeroed, these indices will be zeroed out. So hence you will just get 20, 0, 30, and 0. And let's also go through this example for GPU 2. In GPU 2 you have these three indices, and your range starts from 3 to 5. So first we'll create a mask. So you have indices 1, 4, 2, 5. So first we'll see, does 1 lie range in the range of 3 to 5? No, hence false. Does 4 lies in the range of 3 to 5? Yes, true. Does 2 lies in the range of 3 to 5? No, hence false. Does 5 lies in the range of 3 to 5? Yes, hence it's true. So you get a mask of 0, 1, 0, 1. And you multiply with this 1, 4, 2, 5 indices, and you get 0, 4, 0, 5. And now you need to subtract the lower range, because like this is whatever indices we'll be doing on this GPU, it's not relative, and you have a smaller version of this embedding matrix, so you cannot keep these original indices. You need to adjust for that your range actually starts from 3. So you will just subtract it, and not to go less than 0, you'll just keep a max. It's like you subtract 3 from all of them, so you'll get back 0, 1, 0, 2. So based on this you will get the indices again. And so 0, on the 0th index it's 40, hence it's 40 here. On the first index it's 50, so 50 is here. And it's again 0, so you take 40, 40 is here. Again the second it's like 60, 60 is here. And then we need to multiply the mask again with this embedding matrix, because else these zeros will be treated as the first index. So if you just multiply with the mask is this one, and this will be 0, 50, 0, 60. And now you have computed the embeddings on two different GPUs. Now you can do an all reduce communication, where you add these two matrices and then send it to all the GPUs. Now you would basically have the entire matrix embedding matrix that we wanted initially. So this is how vocab parallel embedding is done. Okay, now beyond tensor parallelism, we have another thing that we always do with tensor parallelism. Is called as sequence parallelism. And let's see the reasoning behind why we need to do sequence parallelism, and how does it fit in with tensor parallelism. Because in most of the code base, if you're doing tensor parallelism, it's always good to have sequence parallelism, and it can reduce the peak activations memory. So in our tensor parallelism, we talked about the embeddings layer, we talked about attention, we talked about MLP. But two things that we didn't talk about is dropout and layer norm. So if you look at these two operations, in dropout, like we drop out some of the connections in the hidden dimension, like our matrix is of size batch size, comma sequence length, comma hidden dimension. So let me go back to our first slide. Yeah, so our matrix is basically batch size, sequence length, and hidden dimension. And so when you do drop out or layer norm, so you are basically operating on this dimension, the hidden dimension. So in dropout, you will drop out some of the uh, elements in the hidden dimension, and you which will make your training more robust. And in layer norm, you will basically take the mean and variance across this dimension. So if you see here, the sequence length doesn't play a role here because all the dropout and layer norm are independent to the sequence. So so you can technically perform dropout and layer norm in different GPUs, and as the operation of dropout and layer norm is independent for each sequence token ID, so you don't need the entire sequence length in a GPU to compute the dropout and layer norm. So let's go back to our slide on sequence parallelism. And so sequence parallelism is generally applied for dropout and layer norm. And as I explained, like dropout is basically on the hidden dimension, and layer norm is also on the hidden dimension, so we don't need technically the sequence length to be materialized. So now let's see the flow of transformer and how how tensor parallelism and sequence parallelism play a role here. So as I said, like for layer norm, you would have sequence parallelism. So it will be better if you follow from here. So suppose you have um, this matrix, and you you first did a broadcast, as we do in column parallel. The first communication is a broadcast. You have two two data points in two GPUs. So these two streamlines mean you are working with two GPUs. So you first do a column parallel, and you multiply the weights with these two duplicated input matrices, and then you apply element wise nonlinearity, and then you get back this uh, matrices which are basically like hidden dimension divided by 2. So if I just zoom in, so this is as we had in column and row parallel. If you see this, so this value after the first column parallel is basically half the size of this input matrix, and this value is also half the size of this input matrix. So it's already sharded for you, uh, so hence you see this h by 2 here. And then we do a row parallel linear layer forward, and you get back uh, different outputs. And here you need to do, if you didn't have to do um, um, if you didn't have to do a sequence parallelism, here what you have to do is like do an all reduce, as we saw in row parallel. You just like add those two matrices, and then s- sh- share that with all the GPUs. But you can see here that we don't want to materialize the entire sequence in a GPU. We as layer norm and dropout are just based on the hidden dimension. So this GPU can focus on the first sequence length uh, indices, and this GPU can focus on the next set of sequence length. So that's why you see S by 2 here. And the operation would be reduce scatter, because in reduce scatter, you if it was all reduced, you send the same data to all the GPUs. But in reduce scatter, you can send half of the data to another GPU and half of the data to the other GPU. So so if you do this, then the each of these sequences would have uh, ha- each of these GPU, each of these GPU would have half of the sequences instead of having the full sequence. And as we saw, like activations memory like grow with quadratic sequence length, and and that would spike up your activations memory in a GPU, in a memory limited GPU. So you would like to have sequence parallelism whenever you're doing dropout or layer num, and the main reason is uh, it's an operation done on the hidden dimension, which is the last element, last size in this matrix, and this doesn't depend on the sequence. So you can technically do a dropout or layer num just for sequence, with sequence parallelism, and you can reduce the memory peak. Now let's go through the code in the RL2 library and try to see how tensor parallelism and sequence parallelism is applied in if you are using FSTP. So if you see here, let me zoom in more. We write a parallelization plan, and if you see here, we start with input layer norm with sequence parallel, and this post attention layer norm is also sequence parallel. Like as I said here, uh, like dropout and layer norms are the places where you would like to have sequence parallelism. uh, so you would basically do sequence parallelism for this layer norm, and uh, uh, this is like a llama layer, and it doesn't have dropout, hence we don't see the dropout here, but you can definitely add it to be a sequence parallel too. And now let's come to this, how we are doing tensor parallelism on the QK and V matrices. So if I go back to my attention slide, let me start the slide. So as I said here, like attention has a good property of dividing into different heads, and each heads can reside in a GPU, so you can have those distinction. And now we need to explain why it is written column wise parallel in the uh, pipe parallelization plan. So the weight matrix for different heads is generally defined like this. Here it's your uh, like the row, and this is the column. So this is the projection head for WQ1, and this is for WQ2. So if you divide here with column, you will get back the weight matrices for each head. So hence uh, you will see here it is written column wise parallel for the Q, K and V. Now the output projection is what comes after you do the attention multiplication, and you get back the same input matrix size. And if you see here, so this is going to be row wise parallel, because you have column wise parallel and then you would have a row wise parallel. And if you see here the output layouts, like it has a shard of 1. So why shard of, so here shard takes a dimension attribute. So shard of 1 means we have, remember, like we have uh, a matrix which is of size batch size comma sequence length comma hidden dimension. So whenever we take an output from your output projection matrix, uh, this is named output layer. So we, as I said, like to do a sequence parallel, we need to divide along the sequence dimension, and as sequence dimension is on the first index, as you can see here, so it is doing a shard of 1. hence it's doing a shard of 1. So if you do a shard of 1, this can be easily processed by this post attention layer norm, and this is going to divide the sequence based on the number of GPUs you have for tensor parallel group, and this is going to just divide the sequence length, and you can do sequence parallel after that. And this MLP is basically what we explained uh, in here, where this was the column parallel size and this is the row parallel size. And generally we also have another matrix that does another type of transformation, so that also needs to be column parallel, because those two needs to pass through GALU and will be processed through this down projection matrix. So if you see this, this is a sequence of column parallel and row parallel, and this is also like this up projection uh, and a row wise parallel. So this MLP is designed a little bit different, but yeah, if you say this, like the up projection matrix is column parallel and then down projection is row parallel, because as you saw, like column and row parallel incurs less communication cost. So if you just define this parallelization plan, then you have basically for each llama decoder layer you would have a parallelization plan for each of this layer, and then you can do the entire forward and backward pass with FSTP. Thank you.